Thank you very much. It's very nice to be here for the first time in the Georg Institute. So let's go ahead. No. Okay, yeah. I guess it's better. Or okay. Thank you. Well, I will begin with remembering what is a spatial set, probably. So, oh my gosh, it doesn't work. Okay, so this is a very well-known illustration by Escher. It's like all his work was about impossible perspectives, and in some sense, a spatial set is impossible to see or visualize it. So we say that A is a Vitali set if it is the range of a selector, or in other words, is the set of representatives of the equivalence relation given by this thing here, defined over the reals. A Sierpinski set is an uncountable set of reals such that it has a most countable intersection with every null set. Lucene set is an uncountable set of reals which has at most countable intersection with the ideal, with every element of the ideal of the Borel-Niger set. A Bernstein set is an uncountable set of reals such that it has intersection non-empty with every perfect set, and its complement is also meeting at every perfect set. And a Hamel basis is a maximal linearly independent set, which we consider when we consider R as a vector space over Q, and a Bernstein basis is a Hamel basis which intersects every perfect set. So it's easy to see that every Bernstein basis is also a Bernstein set. So there are some classical results inside ZFC. So, for example, if there is a Hamel basis, then there is a Vitali set. Well, I say this already. And if we have a model of CFC plus CH, then we can construct a Lucene and a Sierpinski set. Here in this proof, we use that a little bit stronger form of CH. I will see this later. So, and Bernstein proves as well that in ZFC there is a Bernstein basis. All these classical constructions were obtained by assuming the existence of a well-ordering of the reals, or assuming CH under a little bit strong form, that is that R may be ordered with order type omega 1. So there's a question here. Is there a model in which we have all these pathological sets, but there is no well-ordering of the reals? So Pincus and Pickry solved this problem partially. So they say that, that in the Cohen-Hyper-Levy model, there is a losing set, and as well there is a where is the chalk? Here. Okay. So this model, I forgot to put this here. So this model H, let G be generic for this forcing. This is the product of omega copies of coin forcing with finite support. Then H and let A to be the set of all these coin reals added by G. And we take H like the hot of A inside L of G. This is the coin hyperleading model. Dependent choice fails badly because there is no I mean, in this model, there is no countable subset of A. So Pincus and Pickry also asked if whether it is possible to produce as well a Hamel basis and without having a well-ordered reals. So this result is by Mariam and Ralph and Du and you. And here in this model, there are same set as well, but there are no Sierpinski sets. So here is the definition. Sorry. Basically. Okay. So the question now. Can we produce Hamel bases and all these weird sets, but simultaneously, and even though don't having a well-ordered reals? So we ask this question. We construct a model containing all these sets, but in which the reals cannot be well-ordered. So we proceed to construct this thing. Okay, this is a Lego version of these perspectives of Asia. So this lemma is very well known. People here work a lot in forcing. So if we have a forcing notion with the Sachs property, then the null sets in the generic extension can be covered one by one by a null set coded in V, and the same holds for the meager sets. For every meager set in the generic extension, there is a meager set in the ground model which cover this initial set. So as a corollary of this lemma, if P has the Sachs property, then P preserves the losing and the Sierpinski sets. So, in particular, if we take the countable support product of omega 1 copies of Sachs forcing, and we force with it over L, then in this model, the losing and Sierpinski sets that live in L are also losing and Sierpinski sets in L of G. Okay, so now we actually define a forcing notion adding a Burstein set, a Burstein basis. So we define this force in the following way. So for each element in this forcing notion, there is some real such that P is in the constructible universe above X, and in this model, P is a Bernstein set. So, and we order this set by inclusion. Sorry. So, it is very easy to see that PB is non-empty. So it's basically the same construction of a Bernstein set in a model with in L, for example. And here there is a subtly thing that the extendability of PB is not obvious. So we had to make use of a very strong result. So by extendability, I mean this property. So if we have an element here and the X associated with this P, and if we take a real inside this model, L of X, Y, which is not in X, then there is some Q stronger than P, such that P is a Bernstein basis over this model. So I remind quickly the Marszewski idea. So yesterday Omar talked about it. As said is in here, if for every perfect tree we can find a thinner and smaller tree, and smaller perfect tree such that the branches are not in X at all. So it is clear that this is a sigma ideal which doesn't contain any perfect set, and that every set of reals of cardinality less than continuum is also here, but also there are some elements in there which have cardinality continuum. So this property is also important. So we say that this pair of models of CRC satisfies countable covering if every set of reals in the bigger model countable can be covered by a set countable in the smaller model. So this theorem is crucial here. So if we have a pair of models satisfies countable covering, then for every perfect set in the bigger model, there is an element which is not in M. But this theorem can be improved. Actually, in the paper by Groszek-Schleiman, or whatever the pronunciation is. So this is the stronger version. Actually, if W is an inner model satisfying the continuum hypothesis, and the reals in both models are different, there is something here that isn't here, then the smaller model actually are in this idea in the Mazukibis. So we use this strong version. Actually, Ralph produced a very nice proof about this. So if we have two reals and Y is not in L of X, and we have a countable set of reals in this model, then the linear space generated by the reals that we had before and in this idea. So I gave very quickly sketch the proof, and then I guess I can simply jump it because otherwise there is no time. Okay, so with this result, we prove this one, that is the important one. So if we have a linearly independent set in here and some x, then we can find y, which is, and we take a y that is not constructible between x. Then there is some p, there is some bursting basis p extending this little p. So we proceed by enumerating of the perfect sets and the reals in this model, and we define as a sequence recursively, and we are finding some inside each of them, which is not in the space generated by these former ones. And then we define this. And, well, okay. Of the construction, we have that this pi sorry. Okay. So for each c here bigger than the b that we constructed before, being a Hamel basis, we take this element, enlarge a little bit, and by construction, this is a Hamel basis for this space. And in fact, this perfect set all these perfect sets are cutting this P. So P is a bursting set in L of xy. We have some further properties for this forcing. So, for example, under these conditions that are easily verified in this Sachs model of the countable superproduct of omega-1 copies of S, Sachs project. So in these models, we have these conditions, and within this and the former lemma, we can prove that PB is omega closed. So we are not adding any new reals. Okay, let's say this. And there is a very important property of this forcing. After doing all this computation, we can say that this definition is actually a sigma 1,3 definition of this forcing. So this is very important. If we consider this as being the canonical name for the generic bursting basis added by the forcing, then being an element in here is actually a sigma 1,3 statement. So this statement is absolute between class size models of set theory. So we arrive to the main theorem. We take a generic for the countable superproduct of omega-1 copies of Sachs forcing over L, and then inside this generic extension, we force with PB and take this base added by this forcing here. And then we take this model, L of R of B inside this generic extension. Then, in this model, there is no well ordering of the reals. So I try to do a sketch of the proof. So B is indeed a bursting basis, even in here and in this generic extension. And okay, of course, this holds by the extendability and the fact that this is omega closed, so we are not adding new reals after the stack. We proceed by contradiction. We find the P forcing that statement. And yeah, we replace this B by its sigma 1,3 definition here. Then we use that this forcing is weakly homogeneous. So basically, we take a new generic over the tail, which is mutually generic with this tail. Okay, and then we complete this by forcing with PB. So, like the reals that we are, like the reals in here, in this new model, are different from the former one. We localize this at some stage by the Sachs forcing, by the product of Sachs forcing, and then there is a real listed here, and in the other model that is different. So let's say in one case, this real evaluated in N is I, and in the other case is 1 minus I. So we can find these two conditions here, satisfying these two contradictory statements. And we complete this forcing by using that this product is isomorphic. So at the end of the day, we found these two elements. And then by extendability, we found some Q stronger than these elements. And Q actually is living in this model. So that's a contradiction. And well, we have this, the main theorem I said before. So in this model, holds dependent choice because the omega sequence in W of the generic extension are actually in W itself. So here, as PB is omega close, we have the W, see that B is a bursting set for the real set. And in W, we have a bursting set and a Hamel basis. So there is a vital set. The bursting set and the Hamel basis is simultaneously the bursting set, of course. And as in L, there are Lucent and Sierpinski sets, then in L of G, there are Lucent and Sierpinski sets, and as we are not adding new reals in this big model, also the Lucent and Sierpinski sets are there. And as we saw before, there is no well ordering of the reals in this model. So that's, yeah, and thank you very much for listening.